So coming back to our talk, that was the intro basics, and now we'll go over some other basic concepts. It might seem a little disjointed, but it's just because I just want to get all this out there. And then when we're doing more coherent, meaningful talks about other things later, these concepts will come in very handy. Okay, let's just talk about the magnetic response of matter to anything. These terms are very confusing: diamagnetic, paramagnetic, ferromagnetic. So you may have a question on the test. Diamagnetic is when a material weakly opposes an external magnetic field. Think the magnetic field dies inside of the just inside of the material, kind of like every time you think about MRI Physics, a little piece of you dies inside. Now, everything has a diamagnetic effect according to Lenz's law. Just the motion of orbital electrons will necessarily oppose an external magnetic field. So there's always, as long as it has electrons, so obviously not plasma or something like that, there's always going to be a diamagnetic effect. So what are things that we call diamagnetic, though? Water, organic compounds, and that's because the only effect we can see is the diamagnetic effect, because there's no para or ferromagnetic effect. Without further ado, the paramagnetic effect is when a material weakly enhances an external field that it's in. So think of it as a pair of magnets. There's the external magnetic field, and then there's a slight boost to the magnetic field that's developed by that material because of paramagnetism. Examples are oxygen, gadolinium, some blood products. Now, this is caused because there are unpaired orbital electrons. Remember, there's a bunch of fundamental physics going on here, just like with our nucleons. When it was unpaired, it causes signal. So if you have unpaired orbital electrons, then that's when you start getting paramagnetic effects. For example, in the reason we use gadolinium, it's actually a pretty interesting lanthanide element because it has 7 unpaired electrons, which is basically as much as you can find in nature. Now, the paramagnetic, and we call it paramagnetic because when there is a paramagnetic effect, it's about 100 times stronger than the inherent diamagnetic effect that everything has. So if there's any unpaired electrons, you're going to call it paramagnetic because you're never going to see the diamagnetic effect. The third is ferromagnetic. I've capitalized the Fe because think Fe like iron, right? So iron filings or things like that are ferromagnetic. Also cobalt, nickel, neodymium, things like that. This is a really strong effect. This is 1,000,000 times stronger than the diamagnetic effect, although it's much less commonly found. And it's because of the superstructure of the way this element or this compound or alloy or whatever it happens to be organizes itself, and you have these things called magnetic domains. Not only is it much stronger than the paramagnetic effect in its ability to reinforce or strengthen an external magnetic field, but also when removing it from the external magnetic field, you get permanent magnetization. So those refrigerator magnets, those are ferromagnets. Okay. All right, well, yeah, so why does any of this matter? Well, we assume that the external field is constant and uniform and that gradients are perfectly linear. This is obviously never the case, just based on the equipment. But then also, depending on what you put in the magnet, right? You put a person in the magnet made of water and carbon and all this other good stuff, most of which is diamagnetic. And so if you look at the magnetic field lines, there is some bending and some warping. And according to the Larmor equation, anytime you have bending and warping of the magnetic field, because the B is going to be slightly different at slightly different positions in space, that means your precessional frequencies are going to be slightly different at different points in space. And as a result, your RF pulse isn't going to activate evenly. You're going to get dispersion of your spins once it's in the XY plane. It's going to cause you to lose signal. All sorts of stuff happens. So obviously, diamagnetic effects are the least important. Paramagnetic effects are stronger. And then ferromagnetic effects are, destructive, like that image I showed you with the dental work. There's ferromagnetic material on there. Uh-oh. Technical difficulties again. Anyway, yes. So this will cause imaging artifacts, incorrect localization, loss of signal due to star decay, all those things we already talked about. All right, if I can get a little bit philosophic for a second, this should go without saying, and it's fairly obvious, but I want you to think about this in a very, outright way. What is the purpose of radiology? What is it that we do? Okay, what we do is we take a real space or something in existence that's real in the universe. We apply technology to it. And through the application of that technology, we extract information about that real space and present it in an imaging space. Again, this sounds very simple, and like, why are you talking about this? And it's because, especially when we go, talk about X-rays and CTs and stuff, it's all applicable everywhere. So think about it for a second. Real space versus imaging space. Now, real space is three-dimensional, obviously, like you and me. Image space is two-dimensional. I put a plus minus there, not just because we have rendering techniques that trick you into thinking it's three-dimensional when you're looking at a two-dimensional display, but also because we have three-dimensional printing and all that other crap, but whatever. Imaging space, we call it two-dimensional. There's infinite scaling detail in real space because it's real. If you look at my thumb, you see a thumb. If I look at my thumb, I see my thumbprint. If Logan were to shave off the top of my thumb, put it under a microscope, and zoom in 1,000 times, sorry if that was too graphic, then he will see individual cells, right? So there's constant scaling. You keep going down, you'll start seeing the electrons, whatever. If I took an X-ray of my thumb, right, then you see the thumb, and if you zoom in 1,000 times, what do you see? Nothing. A single pixel that's huge. So there's always a limiting spatial resolution in imaging space, which is critical for us to be thinking about. And in real space, real things have all of their physical properties because they exist in the universe. Whereas in the imaging space, we're usually, like I said, through the application of technology, extracting information about the real space. So usually that's only one parameter, like density in CT, for example, or X-ray, or more accurately, linear attenuation coefficient. So then we're at the center of this, and what does the radiologist do? Well, we have years and years of experience. We trained for so long, basically watching countless examples of the imaging space resulting from our applied technologies that we understand. And we become like a translator, basically. And so, we're experts in saying, in interpreting this imaging space, right? Because it's not apparently obvious where it comes from or what it represents in the real space or the real three-dimensional world. Okay, now, how do we translate real space? So this starts to become, there are complicated ways in thinking about this, especially when we start thinking about how do we interface it with those technologies. Well, a central concept is spatial frequency that always throws people. So I wanted to include it this time in this talk so we can start thinking about it from the get-go. Okay, think of a regular frequency, right? The word frequency, what does frequency mean? It means how often something happens over time. Well, as usually happens in English language or in any spoken language, we develop heuristics for ease of communication, and the word frequency is actually just a shortened form of the appropriate word, which is temporal frequency, because you can have any kind of frequency, including spatial frequency. So, talking about temporal frequencies, we'll just look, this is a sine wave, right? And so this is representing some amplitude over time, right? And then we have a low frequency, which is a long wavelength, and then here's a sine wave that shows us a slightly higher frequency. So more things are happening over a period of time. Okay, so stick with me. The spatial frequency is exactly the same thing, but over space instead of time. So picture a bookshelf, like the one behind you or here. Say it's 1 meter long. This top row holds about 25 books, okay? Now, for the second row, if we take all the books out and put them back, obviously those aren't the same books. If we put them back but face out, well, now we can only hold about 6 on that shelf. So, okay. Well, let's try to describe these bookshelves in terms of spatial frequency. The spine-out books have a spatial frequency of 25 books per meter. The face-out books have a spatial frequency of 6 books per meter. Does this make sense? Right? Okay. So alternatively stated, within this space, I know it doesn't seem relevant, but trust me, it is. Within this space, both the real space and the imaging space representation you see here through the projector, the spine-out books are a high spatial frequency feature of this image, and the face-out books are a low spatial frequency feature of this image. That will become very important later when we talk about Kspace and edges and stuff like that. Okay. Now, let's take this one step further, and instead of things like books, per meter on a shelf, let's say you're quantitating a parameter. Let's say now density, just because it's easy to think about, as it varies over position, right? And so here we see there's, Here's a variation in density where the density gets higher and higher, over 2 centimeters and then, lower. So we have over every couple centimeters, we have a large density fluctuation, or we have a small density fluctuation over a much smaller spatial scale, right? Now, if I were to map 256 grayscale values, color values, to these data points over time and display them, then I would be showing you a visual representation of the different spatial frequency features, which presumably I've extracted from a real space somewhere, right? It's an X-ray, right? So this high amplitude, low frequency spatial variation of density could be, say, ribs along, a chest wall. This low amplitude, high frequency, say, could be alveolar walls between alveolar air spaces. So this is, as promised, relevant, but can be very difficult to think about. So, Steve, if you ask me, can we measure the relative distribution of resonant hydrogen nuclei instead of density like we talked about in a real three-dimensional space, say a patient, as a collection of spatial frequencies, which later we'll learn is Kspace, and then somehow transform it, also talk about that, in an imaging space as a 2D array of grayscale values? Can we do that? I would say, well, yeah, of course. In fact, that is one of the most concise descriptions of MRI I've ever heard. Good job, Steve. So, and that's why I want to talk about all these things, because if you really think about the process of what we're doing, sometimes it can help you and guide you conceptually through think about these things. Now, I did use the K word in the last slide, and I know a lot of people are afraid of Kspace, but really, Kspace is just a plot of spatial frequencies, which we've already described, so hopefully they're a little less intimidating now. It's a 2D plot for an image, a 2D plot of XY coordinates. Each XY coordinate corresponds to a different combination of spatial frequencies as they vary in the X direction and in the Y direction. Okay, so, and then the value at that XY point is the relative weight of those frequencies in the imaging space. That's a little hard. Okay, I might have lost some people, but so think about it. And in an imaging space that's rich in high spatial frequency filters, that top shelf on the bookshelf, is going to have more amplitude at high X and Y values, thus in the periphery of the 2D Kspace plot. That's where your high spatial frequency information is. An imaging space rich in the low spatial frequencies, the face-out books, is going to have more amplitude at lower X and Y values. Low spatial frequencies are found in the center of Kspace, where X and Y values are small. Everyone follow that? Okay. So that's and a little bit more in Kspace later. So how do we decode? Let's kind of jump forward a little bit. The summed oscillating signals. Remember, when we take an MR image, every single thing that's happening inside that bore is summed together. Every single proton. There are billions, trillions of these things. They're all stacked on top of each other. We just listen to one signal coming through one antenna. So how the heck do we parse all that out? Well, Fourier Transform to the rescue. Now, I know this looks complicated, and we aren't going to focus on the equations or anything like that. But Fourier Transform allows us to move between real space, Kspace, and our imaging space. So to look at the interplay, real space, that's our patient, is going to have qualities that vary over distance. Kspace is a plot of spatial frequencies as they vary. An imaging space, then when we recreate it, is going to again vary over distance, but in a 2D way, like we talked about with only the extraction of the details we're focused on. Thankfully, one of the mathematical properties of Fourier Transform is it's reversible, so you go back and forth. Thus, we take a real space, right? A human being is a structured spatial frequency variation of protons. Okay, and when we do the MRI, it translates it. It's a very convoluted argument. It's very interesting, but I'm sure I put everyone to sleep. The MRI is actually, when you perform an MRI, it's actually a practical, real world, in the real space Fourier Transform. So the data you collect is in Kspace. And then, once we have the data on paper, we apply the Fourier Transform again to Kspace, and that's where your image comes from. Because Fourier Transform is reversible, you translate the human body into Kspace data, and then you Fourier transform the Kspace data, and you get an imaging representation in return. Okay? Now, the Fourier transform itself, again, we won't focus too much on it, but the central theorem is that any function, technically any continuous function, can be described as the sum of sine and cosine waves of different frequencies. So here's an example. If we were to take this curve here, right, and we were to try to approximate it, all right, so we take a cosine wave and we say, okay, well, that doesn't look like it at all, right? Well, let's take a second cosine wave, that's some different features, and add it to the first one. So the sum of these is where you see approximation 2. That's actually getting pretty close. So we take another frequency, a third fundamental frequency with a different weight. Notice this has a certain weight, that has a much higher weight. This has an intermediate weight. Well, this is getting pretty darn close, and by the time we get to the fourth fundamental frequency and we've added them all together, we've actually completely recreated perfectly this wave, which otherwise looks like nonsense, right? I'm going to show this to you again, but sort of in the opposite order. Another example first. This is me trying to figure out Fourier transform a couple years ago. If you have this square wave function, right, you start with an approximation, say just a flat line. You add a sine wave over it, right? That's the 2 terms, and then you add another term. So we're adding more and more fundamental frequencies, 3 terms, and then by 7 terms, that's looking pretty much like a square wave, right? So this is a very powerful technique, Fourier transform. Let's see some examples. Take it down a notch, make it a little simpler so we can see what it's actually doing. So here's the sine wave generated in Excel. And if you Fourier transform it, then you get this in return. What does this mean? So the height, the y-axis, are relative amplitudes, and the x-axis is frequency, right? So a sine wave is just a single frequency, and that's why there's a spike. Now, why are there 2 spikes? Because positive and negative, Kspace is actually symmetric. And since it's radial and oscillatory, positive things are equal to negative things. So you get 2 spikes for that. Now, what if we took a sine wave of a slightly higher frequency? Do the Fourier transform, you're starting to see, a trend here. Same thing, even higher frequency. We see that whenever we have a single wave, we're just going to get a single spike, which is at that fundamental frequency. And it's Kspace is showing us this is, right, small numbers, low spatial frequency, or low frequency something, higher frequency something. Okay. Now, just for funsies, what if we added those 3 sine waves together? What would that look like? You can't really do it in your head, right? Because you end up getting this. What the heck, right? So, and if I were to show you this, you would be like, I don't know, it's just some squiggle. You would never guess that that's 3 simple sine functions added together. But this is what it looks like. Well, that's interesting because this kind of reminds me of, say, a real space that's a collection of different spatial frequencies. And, you don't know, you can't make heads or tails of it. So how do we decode it? Any thoughts? Fourier transform! Yeah, everyone's favorite. All right. Yeah. Shouldn't say no. All right. All right, so if we, this is a real plot generated in Excel with experimental data from adding those 3 sine curves together. And Fourier transforming that real data set gives us this. Well, look at that. There's 1 pair of spikes for each contributing sine wave, just like we saw on the last slide. So this is amazing technology, and it works. And it's very simple. I shouldn't say that, but yeah. Anyway. All right, so now, that's 3 simple sine waves. If you have tons of different sine waves right now, so imagine a real space, right, a real body with all these protons spinning all kinds of different frequencies, almost so that there's a continuous range of precessional frequencies. When you sum those together, take my word for it, it looks like this. This is called the sinc function, okay? And I want you to show you this because I'm going to have this function up in a lot of the other talks, and you're going to be seeing it over and over again. So don't be intimidated by the fact that someone put a C after the word sine. It's just another function. This is what it looks like. It tapers off. It gets dampened in the extremes, and it's a very high central peak. When we collect MR data, this is what it looks like. If you plug an oscilloscope into the machine, when you're taking an echo, it looks like that, okay? Or it looks like this. And the sinc function is just a composite of multiple other sine and cosine or sinc collections at different fundamental frequencies, right? So see, the red is a low frequency, green is intermediate, and blue is a high frequency. Add those together, just like I showed you with the sine waves, specifically in odd harmonics, you'll get exactly back a sinc function. Okay, so why does this matter? Well, the Fourier transform, when you have more than three, all these things, instead of just a collection of spikes, you start getting basically a rectangle, because you have a continuous range of frequencies, okay? This is how an RF pulse is generated. We're going to talk about this a lot more later, but you all heard the term bandwidth and been like, what the hell is a bandwidth? You know, and this is what a bandwidth is, right? The bandwidth is a range of frequencies. That's all it is. So when people say, change the bandwidth, use a higher bandwidth, use a lower bandwidth, what they're saying is, listen to a wider range of frequencies so that when you receive this sinc function and you're Fourier transforming it, you are looking at these discrete underlying fundamental frequencies in their relative weights or contributions. So in an RF pulse, we send out all these frequencies at the same exact intensity, right, which is a nice square wave, which gives us a perfect sinc pulse. But from a real body, since there's obviously supposed to be differences in spatial distribution, otherwise you'd have a great image, when you get this back, when you get like we'll call it the wonky-eyed sinc function, when you get the wonky-eyed sinc function and you Fourier transform it, instead of a perfect square wave, you're going to get a histogram, right? So each fundamental frequency is going to have a different amplitude, which is related to its relative weight or the presence of that precessing element in the imaging space. That's a lot to say. I don't care if you're lost, because I just went way above and beyond and way out there. So we're going to return to these things and talk about them more, especially next time and the time after. But if you heard it once and got confused, next time you hear it, at least you won't be like, whoa. You'll be like, okay, I've heard this before. So all right, so that's some fundamentals that are going to set us up for success in the future. And then, this is just a cool picture of the Fourier transform kernel. And it's question time, so we can go over some questions. These are going to be like sample test questions, but they're really good to like check your understanding, and we can discuss about them. All right, so by definition, the craniocaudal dimension of a patient is said to lie along which direction? In the boarding. All right, good. So Z is the correct answer. X, for our purposes in the future, is going to be left to right. Y is going to be up and down. And B1 is the direction of the RF pulse, right? Okay. Gradient coils are primarily used to do which of the following? Record the MR signal, shift longitudinal magnetization in the XY plane, keep B0 constant throughout the board, or predictably vary magnetic field strength along spatial dimension. D, yeah, that's one of those like, oh god, okay. So the long answer is the right one. Happens to be the case here. But just looking at the other ones, so D is correct. Record the MR signal, that's the receiver coil. Shifting longitudinal magnetization into the XY plane, that's what the RF pulse does. And keeping B0 constant throughout the bore, that's called shimming. You might hear that term. There's active and passive shimming. When Siemens or GE or whoever first sets up a magnet, the B0 is definitely not constant. It's nowhere near constant. It even interacts with the room, and it's crazy. They go in there, they do all these tests. It's really neat to see, actually. And they have passive shimming, which actually there's a bunch of little trays inside the magnet that have little iron weights in them, and they like do this for hours and hours at a time to try and even out B0 as much as possible. Once they're happy with the passive shimming, they let you play around with it. And then, when you're actually scanning, you've seen people shim before. And what they're doing is they're just adjusting the frequency at which they're sending out RF pulses and listening. And in some cases, when you're using a shim volume, they're actually like kind of altering the magnetic field using gradients supplementally. So kind of neat, but has real life purpose. Okay, so in the classical model, remember that's the spinning top model, an RF pulse must be emitted at the Larmor frequency to be effective. In the quantum model, that's the flipping back and forth model, the spatial frequency is equivalent to what? B0 times the gyromagnetic ratio, the flip angle of B1, the energy difference between the parallel and antiparallel states, or about 9 protons per million at 1 point. C, very good, yeah. So we talked about this before. It's just the energy difference is basically the same thing as sending out an RF pulse at the same frequency. All right, so now we're going to start thinking about signal. I really want you guys to get this one. So, okay, a cup of pure water is in a 1.5 Tesla scanner for 30 seconds. It means it's been sitting there for a while, okay? A 90-degree RF pulse is applied. Immediately after, there's a transverse magnetization, NXY1, okay? At 3T1 times later, as defined by that water, a second 90-degree pulse is delivered, resulting in MXY2. Which of the following is a true statement? MXY2 is slightly less, MXY2 is slightly more, MXY2 is much less, or MXY is much more. Slightly less, very good. In fact, it's exactly 95% of MXY1. So what the point of this was to show you that if you have multiple RF pulses, it takes an appreciable amount of time, as defined by T1, for that signal to recover. So if you develop magnetization in the transverse plane with an initial RF pulse, that might be all well and good. But if you got to keep repeating this at a certain TR, it may not be sustainable. So you have to think about these things, right? And if you've waited 3T1 times, then you've let the longitudinal magnetization recover to 95%, right? So you're going to thus develop 95% of the same transverse magnetization on that third pulse. Make sense? That'll also be necessary when we start talking about image weighting and contrast. Okay, so if a person is within a 1.5 Tesla MR for 30 seconds prior to applying a 270-degree RF pulse, so think about that, which of the following most accurately describes the magnetizations immediately after a 270-degree pulse? MZ equals 0, NXY is 3/4 the max of the NXY. MZ is at a max, and NXY is 0. MZ is equal to negative MZ, and NXY is 0. Or MZ is 0, and NXY is the max. I want you to apply what you think. Yes, very good, D. So 270 is the same as a 90, right? Because when these all describe different things. When MZ is 0, well, this is something different. When MZ is at a max and MXY is 0, that's either nothing or a 360-degree pulse, right? When MZ is negative MZ and MXY is 0, what's that? 180? Yes, 180, exactly. So because 180, you take out all the, you're just flipping the Z magnetization, and you don't have anything XY. And then, yeah, so 270 is the same as 90. Maximum transverse, no MZ. Okay. When a transverse magnetization MXY is decaying, a 180-degree RF pulse may be used to refocus phase coherence. Right, so we're talking about inversion pulses. Which of the following things will still cause significant dephasing despite the use of a 180-degree pulse? Adjacent surgical clip, spin-spin interactions, B-field inhomogeneities, or a sharp fat water interface? B. Very good. That is exactly correct. So when you use an inversion pulse for refocusing, it undoes all of the structured effects. It undoes all those T2 star effects. So it undoes field inhomogeneity, iron in the tissues, whatever. But spin-spin interactions are completely random and can't be predicted and don't reverse in the presence with 180. Okay. 1 T2 time after a 90-degree RF pulse, MXY has been decreased by 63% of its original value, by definition, right? How much of MZ is recovered by this time? 63%, 37%, 2 T1s worth, or not enough information? D, yes, I'm so proud of you guys. Okay, I'm going to put the mouse down. My understanding of MRI was impeded for about 4 years because I did not understand this concept that I'm about to tell you. MZ and MXY are completely and totally independent. T2 and T1 are completely and totally independent. Nobody ever told me this or knew it. But when you do an RF pulse, 90 degrees from Z into XY, right? Z has gone to 0 and MXY is at its max. Then MXY shrinks and MZ grows. I, for some reason, thought that somehow MXY was shrinking and going back into MZ, that the two were tied. That is not true. That does not happen. Okay, I just want to make that clear because I think it'll help you a lot if you know that. So yes, not enough information. The T1 can be whatever it wants. The T2 can be whatever it wants. MXY can go away as fast as it wants. MZ can recover as fast as it wants. Totally independent. Okay. A material is placed in a uniform external magnetic field, V0. An effective magnetic field within that material is measured slightly less than that of V0. This material is said to be ferromagnetic, paramagnetic, diamagnetic, or supermagnetic. Diamagnetic, just like you study in physics. A little piece of dye inside. It's great. Okay, so yes, diamagnetic, slightly reducing the external magnetic field. Remember, everything's diamagnetic at baseline. Para and ferromagnets, magnetic effects are much stronger, so we'll override paramagnetic. Sorry, diamagnetic. Okay. According to the central theorem of Fourier Transform analysis, any continuous function can be approximated by adding weighted series of sine and cosine functions of different fundamental frequencies. Yeah, I know I just said it, but I wanted to hear it again. So there you go. You had to listen to it again. I love the Fourier Transform. It's so cool. Okay. A population of water protons in the solution of iron oxide are precessing in a 1.5 Tesla MR bore at a rate of 65 megahertz. Approximately how fast will they precess in a 3T Siemens magnet? I forgot to mention the first one's GeV. 8 kilohertz, 33 megahertz, 65 megahertz, 130 megahertz, or 4.2 gigahertz. I wanted to say gigawatts. Back in the future. Anyway. Sorry, what were you saying? Yes, very good, 130, right? According to the Larmor equation, these relationships are linear. So if you double the B, you're going to double the precessional frequency because the gamma, the gyromagnetic ratio of that water in that solution is going to remain constant. Okay. Why is MXY equal to 0 at baseline before there's any RF pulses within the bore of an MRI? Is it because free induction decay is too rapid? Is it because the moments aligned with the z-axis are in phase? Is it because the spatial frequencies will cancel one another? Or is it because moments aligned with z-axes are out of phase? D. Which one? D. Yes, D, not C. Yeah. So spatial frequencies cancel one another. That's just a distractor that kind of doesn't really make sense. Free induction decay is too rapid. Well, this is before any RF pulses, so free induction decay has nothing to do with it. Yeah, so the moments that are aligned with the z-axis are out of phase. And since they're all out of phase, they're randomly distributed, and there's millions of them. So the x and y components of each one is going to cancel out. It's not until the RF pulse is applied that they gain phase coherence and create a real magnetization in the xy plane. Okay, I'm performing a spin echo sequence because I want to maximize the signal on a T2 image. 60 milliseconds after my RF pulse, I send out a 180-degree refocusing pulse. When is it that I will collect the maximum signal echo? 65 milliseconds, 90 milliseconds, 120 milliseconds, or 240 unitless dims? Sorry about that. Obviously, not the right answer. So, 120, yes, very good. Right, because so there's a dephasing happening for 60 milliseconds. There's dephasing due to structured things such as iron in the tissues, B field inhomogeneous, whatever. Send out the 180-degree pulse, invert it. That means they're going to start refocusing. And in order to undo those predictable or structured dephasing, you have to wait the same amount of time that they dephased for. It makes sense, right? The rabbit and the turtle have to catch up exactly with the pig in order to maximize your signal. Okay. Which of the following, we're almost done, which of the following could be considered a high spatial frequency feature of an imaging space? A 2 millimeter spaced grating on a test phantom, say in an X-ray, the MR signal intensity of a 1 liter bag of saline with a small field of view, T2 shading present in the contents of an 8 centimeter dermoid, or high signal to noise ratio in a large renal cyst. A, very good. Yeah, so high spatial frequency, that's something that occurs, a large variation occurring over a short scale of distance. Right? These other things are actually large. So the contrast within that's just a big bright blob. That's low spatial frequency information. It's like no signal on this edge of the image, lots of signal in the center, no signal on the edge. That's very low spatial frequency variation. Okay, T2 shading in a dermoid, that goes from white to black over 8 centimeters in a slow gradation. That is a low spatial frequency. Right? High SNR in a large renal cyst, that kind of doesn't make sense, but if you want to say, well, it's kind of the same as the liter bag of saline. Contrast inherently is a low spatial frequency feature. That's it. So next week, what are we going to talk about? Spatial localization and how to actually put everything together and make our first image. Any questions? Great. That's it.